the number system, computers use different numbers than the one we used. Therefore, you are going to find different number systems that we are going to be defining. We are not going to go into too much details, but we are at least going to mention some of the common ones, and therefore, probably at a later course, you're going to be introduced properly to the number system. When we type some letters or words, the computer translates them into numbers, as computers can only understand certain numbers. Actually, not all numbers, only in certain numbers. A computer can understand the positional number system where there are only a few symbols called digits, and these symbols represent different values depending on the position they occupy in the number. So the value of each digit in a number can be determined using the following: the digit itself and the position. So the digit itself, the position is going to determine the value of each digit. Now, the base, of course, the other thing is the base of the number system, where the base is defined as the total number of digits defined in the number system. To give us a good introduction, we are going to start by defining the very common one that you are already conversant about, that is the decimal number system. Since you are in kindergarten, you are able to learn the numbers from 0 all the way to 9. So 1, 2, all the way to 9. And these numbers are the ones that are called decimal numbers. They fall under the category of decimal number system. And decimal, to start with, is actually, it has an connotation to mean 10. So normally decimal means 10. Therefore, it means that from 0 all the way to 9, these are 10 digits. So 10 digits are the ones that constitute the decimal number system. And therefore, we are saying now that the number system that we use in our day-to-day life is a decimal number system. The decimal number system has base 10. So when we say that it's a decimal, we say that this has base 10. And you'll see what this 10 means. But the most important thing is the base means the total number of digits in that number. Now, of course, it runs from 0 to 9. In decimal number system, the successive positions to the left of the decimal point represents units, tens, hundreds, thousands. This is a concept that you remember you learned very early in your elementary school, where we say that if we have 127.52, you are told that there is a decimal here, and it has some decimals to the right. 1, 2, 4. Then we used to say that this first digit represents ones, the second digit represents tens, the third one represents hundreds, and the third one represents thousands, and the last one represents 10,000s. Therefore, that is what we are saying that constitutes the value. Of course, when you go to the right, we talk about the 10, the 100, and the 1,000. Now, what you're saying is that what determines the value of this number that I have indicated there is first the position of each digit. Number 2, the value of each digit. Position means this is under 10, ones, tenth, hundreds, etc. Those are the positions. The value itself, this is a 2, so this is 2 tens. This is a 4 tens. This is 7 hundreds, etc., etc. So what we are simply saying is that those are the first two elements that determine the value of this number. And lastly is what base is it based on? And you can clearly see that this is based on base 10. And here we are looking at a simple example that we are saying that each position represents a specific power of the base, which in our case is 10. For example, the decimal number 1, 2, 3, 4 consists of digit 4 in the unit position, 3 in the tenth position, 2 in the hundredth position, and 1 in the thousandth position. Its value can be written as this one. So we have 1,000, 200s, 3 tens, and 4 ones. And therefore, when you add them, you get 1,000 plus 200 plus 10 plus 4. You get 1,234. So clearly, there is nothing new from what you are already conversant with. And therefore, I'm just doing this for the sake of introducing the number system. And therefore, as computer programmer or an IT professional, you should understand the following number system. Now we are talking about, so we have just introduced the first one, which is the one that is called the decimal number system, but then we say that there are other number systems, and the first one is called binary number system, and the other one is called octal number system. Binary has 2 digits, 0 or 1, so you might have a number that is represented as a series of zeros and ones. The other number system that we can find is the octal number system. This one is very similar to the decimal number system, but it has 8 digits, and therefore it is said to have your base 8. On the other hand, it has 8 digits that run from 0 to 7. So you find that when you go to from 1, 2, 3 all the way to 7, it will start now counting again, goes to 0 and 1 all the way to 7 again. So the same way we normally run from 0 to 9, the same way we go to 9 and then we start at 10, we normally bring the first digit here, we go to 10, 11, 12, etc. On the other hand, we go all the way to 19. After 19, we take the second digit and we start to 0, 2, 1, etc. So similar way, that is the same thing we do with octal number system. We are going to be running all the way to 7, and then after 7, we are going to have 1, 0, 1, 1, 1, 2, all the way to 1, 7, and then we go to 2, 0. So definitely there are some numbers we are going to be skipping. We are not going to find 8, you are not going to find 9 in the octal number system. Those definitely are missing. So the other number system that we are going to come across is hexadecimal number system. This one has 16 digits that run from 0, 1, 2, all the way to 9. But because these are 10 digits, we require 6 more digits, and therefore we normally adopt digits from the alphabet that run from A all the way to F. And therefore you are going to find that in using the decimal number system, you're going to see that A represents number 10, B represents number 11, C represents number 12, D represents number 13, all the way, and F represents number 15. So that is the hexadecimal number system for you, and it clearly has 16 bases, and therefore we are going to find how it works on that level. So those are the 3 that we are going to deal with first and foremost, and then we are going to do a very brief introduction to each of them, and we are going to start with the binary number system. And the first thing is we said about the binary number system is that it has 2 digits, 0 or 1. Therefore, you're going to find a number that might be represented by many combinations of zeros and ones. And we are going to see how we can be able to convert the zeros and ones to become a certain number. Also, it is called the 2 or base 2 number system. And then, as we said in the introduction, each position in a binary number represents a 0 power of the base 2. Of course, a 0 power of the base. And in this case, our base is 2. The last point we want to say is that the last position in a binary number system represents a times power of the base. An example, 2 times where x represents the last position minus 1. Assume you are given this number 10102 and you want to find its decimal equivalent. Clearly what we are going to do is that we normally split our number, and I can just write it here at the top. See, 10101. This represents the base. We normally put 2 there, and therefore what we then do, we normally start by pressing giving the value of each digit. This is position 0, so we normally say 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, and 2 to power 4. Okay, so then what we do next is to multiply each of these with its value or with its position. And therefore what you are going to find is that 2 to power 0 will represents this is equals to 1. And therefore you see 1 times 1, this is equals to 1. So it gets the value of 1 there. The other thing is we say 2 to the power 1 is 2, but we are multiplying it with 0, and therefore it will become 0. When anything multiplied by 0 becomes 0 there. The other one is that 2 to the power 2 is 4. When 4 you multiply by 1, you get a 4. Similarly, this becomes a 0. And last but not least is that 2 to the power 4 is 16. And you will multiply by 1, you get a 16 there. So we want to find its decimal equivalent, and we are clearly going to see that when you add all of these, you're going to find this is 21, and that is 21 to base 10. This is the normal 21 we know. We ordinarily, when you're talking about numbers, we do not add a 10 here, but now because we are introducing 3 other number systems, then you might find us we are adding a base at the end here, just to tell us that our number is represented using the base 10. The octal number system, as I have already mentioned, it has 8 digits. They run from 0 to 7, and it is also called a base 8 number system. Each position in the octal number represents a 0 power of the base. And this is the concept that we might have missed when we were discussing the previous one, but you're going to see its weight as we carry on. The last position in the octal number system represents x power of the base. Example 8x, where x represents the last position minus 1. The best way to do that is to look at the example, and we have an example here, octal number system. And I'm going to rewrite it again. I know this has already been done here, but I just want to break it down for you. I'm saying 1, 2, 5, 7, 0. And as I already mentioned, this 8 has no value. It only tells you that this number is represented in base 8. We are always going to say that we are going to say 8 power 0. Contrary to what we did with we always take the base to power. So the position is, the first position, we said position minus 1. So if it was position 1, then you give it 1 minus 1 becomes 0. This becomes 0 here. This is going to be 8 to the power 1, 8 to the power 2, 8 to the power 3, and 8 to the power 4. So always remember that we start at 0, 1, 2, 3, 4. So having said that, then the same way we did with the previous example is that you take this value, this is value 8 to the power 0 is 1, 8 to the power 1 is 8, 8 to the power 2 is 64, 8 to the power 3 is 512. So this is 512, and 8 to the power 4 is 4096. And we are saying that this is going to be 4096. So then what we do with that is we are going to say multiply this. You can multiply 496 with 1, you get this value. Then you take 512 times 2, you get this value. You multiply 5 times 64, you get this value. Last but not least is you multiply 7 by 8, you get 56. And of course, you know 0 times 1 is always going to be 0. You find your 0 there. When you add them, you get this value. So what we are saying is that the decimal value of this number is 5,496, which is the normal number that we are used to. But this number was in base 8. As far as you can see it, this number in octal number was actually 12,570. So clearly, the value of this number is less than that of our number that we are used to, which is decimal numbers.